So one of the most difficult things to do in any live steam engine is of course the cylinders, and more specifically the limits and fits for all the various components that need to move together. For example, the piston needs to be a steam tight but mechanically loose fit. The tolerances for that is ridiculous, and most people will tell you that you need to have DTIs, you need to have DROs and all sorts of fancy things. Well, no, you don't. Hey guys, I'm Luca and welcome to my channel. I need a cup of coffee. In this video, I'm going to show you how to machine your cylinders very accurately. And I'm going to do it without using all these fancy gadgets to pick up surfaces and all sorts of nonsense like that. We're going to use the geometry and very simple techniques to machine incredibly accurately. You are going to need a vernier, of course, because that is just the easiest way to measure everything. But you're also going to need a mark, and you're going to use the mark once and then you're not going to use it again. So this is one of those things that I would learn from a buddy. Use it, set up your lathe, and then you're done. So just very quickly before I carry on with machining my cylinders, I will do a decent series on casting. Everything from 3D printing to make my patterns, to how to design patterns, to how to cast, how to break out the molds, how to make your own sand, how to make your own inoculants, etc, etc. But that requires a few videos, and I want to do it properly because I want you guys to give it a bash. But these cylinders required a little bit of lateral thinking, and I want to start planting the seeds as the series goes of how you can use casting in your home workshop to do amazing things. And I'm going to be honest, I've worked in industry in foundries, and I've seen foundries that wouldn't be able to do this. So these cylinders are a typical two-split pattern, easy peasy. The problem is the area that goes around the smoke box, and that is, there's no convenient way to do a split line. You're going to end up breaking the sand by the rib section. Now, a technique that is very seldom used in the home workshop and almost never used in sort of practical foundries because it takes too long, is instead of splitting the mold, you split the pattern. Now, the minute that you split the pattern, now all sorts of configurations can be done in the home workshop. And that is how I cast these cylinders. So where do you start with a casting like this? It's horrific. Look at this. It's got that funny surface from the smoke box. It's got these ribs, the draft angles on the side, so there's no reference point there. All right. Look, with all of my cylinders, what I like to do is I like to machine the valve surface first. And there's a couple of reasons why I like to do that. It's a lovely large surface to machine, so once you've got that reference face, everything else becomes easy because it's easy to clamp, it's easy to hold, but you need to get there first. So you need to find a surface that is convenient to do that first cut. In all of my designs, I always give myself a flat surface in the mold that is a nice as-cast surface to set up on the lathe. And in this case, the bottom drain cock bosses are a very nice surface to set up on the lathe. I also have this convenient long surface to set up. That makes setting this up to machine my first reference surface really easy. So let's start there. So to make a really cool set square that costs you nothing, you just machine a flat on any convenient piece of square bar. If that gets put up against the chuck, you can see if that surface is true. Now, if you can't see any light or any dark on that surface along the full length, you know that that is set up properly. And same with the other side. So this looks pretty good. Now, I've set this up already so that I don't need to bug you guys with tapping and all sorts of stuff on the lathe. But for my setup, it just works out that these two 12mm square bars at that surface, which just also happens to be a flat surface in my design, is perfect for this setup. Now all you do is you tap it until you get your your two positions, and these need to be tight, then you know that that surface is parallel perfectly to the back end of the chuck. And here's a top tip. When tapping in an as-cast surface or anything into a 4-jaw chuck or any setup on a machine that's connected to a spindle, please don't use a proper hammer. I make these little lead hammers that work really, really well. And if you tap it, it's a dull impact, so it's not going to damage the bearings. And you're not going to damage the casting either. So this will be tapped into place, and then these will be removed just before machining. This looks pretty good. Let's do the machining for this. This surface looks absolutely beautiful, and I still need one more skim to get it on size, but let me show you guys a top tip here. There are 4 points that we need to measure, from there to there, from there to there, and then that thickness and that thickness. So typically what I do is I draw a line of where I'm measuring, and then each point that I measure, I either write the dimension or the amount that it's at. So it's plus 0.2 in that case. That's 5.15 plus 0.15. And then because we used these 12mm bars to get to that reference point over there, this will make a convenient place to measure to that as cast surface. 30.1. Now remember, all of these surfaces are as cast surfaces, or to a as cast surface, and this is only a reference surface. So I'm looking for about a 0.1. And you can see at my corners I'm 0.2, 0.15, 0.1 and 0.15. So what I'm probably going to do is I'm going to skim it another 0.15, and that 50 micron that it's going to be slightly out in one of the corners doesn't matter, because this is the reference face and where it's out is an as cast surface. And look, anything between 0.1 and 0.05 on an as cast surface is pretty freaking good. So now when I skim this surface, because that dimension is changing, I don't want to make a mistake and reuse marked dimensions. That's why I'm marking it on this face. So now when I skim it, all those dimensions will be taken off and I start all over again. Then I know that each dimension on the part, as the part gets machined, is the current dimension. It's not a dimension that is legacy and I've machined it off and now it's incorrect. So I always mark the dimension on the surface that I'm machining. That will change that dimension. Top tip. I'm happy with this, and look how nice this casting looks. Fantastic. Before we carry on machining these cylinders, everyone would agree that a cylinder that is not parallel on the bore is just not going to work. On the one side of the stroke you're going to get it tight, on the other side you're going to get it loose, and what's going to happen is the loco or steam engine or whatever it is not going to go nicely. It's going to sort of hunt and it's going to misbehave. Whenever I do steam cylinders on all of my builds, I take out my trusty test bar and I skim it and I check for lathe parallelity. In other words, I check that the bed hasn't twisted over time. And it does. I mean, changing seasons, stuff moves around, the floor moves around, there's nothing you can do about it. Typically, you should be checking this once a season. What I like to do is I check it just before I do the bores of my cylinders. And that typically works out to once or twice a year. I found that my lathe is actually very stable, which is really cool. So we'll check it now and we'll see how close we are. Let's have a look. This is always very exciting because it's interesting to see how much the lathe has moved around over time. So the absolute value doesn't matter, it's just the relative. So that's 30 and 30 spot on. That'll work nicely. So now we have a nice reference surface for our cylinders. This is where things start falling apart, and a lot of builders battle with the next few steps of, well, making cylinders. It's actually very, very simple. This surface, the reference surface, needs to be parallel to the cylinder bore, and then you know that all your rods for your valves and your pistons are parallel and they're running like they should. Another thing that is incredibly important is the piston gland side, in other words the side that the piston rod goes through, has to be absolutely perpendicular to the bore, and it needs to be in all directions as well as perfectly concentric for that cap. This is important because what will happen if you get that wrong, if this piston and sort of rod goes at different angles, is typically it'll be loose on the one side of the piston, but as the piston rod gets shorter and you get closer to the cap, it's going to start sticking. Now typically what the guys would do is they would open the gland and open that sort of hole that the piston goes through. Now I don't agree with that. That hole needs to be reamed size for size so that you don't need to worry about sealing on a gland. I like to seal on holes, not on glands. So all the following machining steps, I have one thing in mind. You need to keep this perfect to the bore, and the bore needs to be perfect to your piston side face. Now I always mark reference which side I'm going to use as the reference surface. So at the end of the day I'm going to have a reference surface there and a reference surface there, and then the bore and everything will work itself out. But before we get there, it's always prudent to machine the other side, and we're just going to get that casting surface more or less right before we flip it around and we do the most critical of the whole cylinder, which is of course that surface and the bore. Now what a lot of guys do is they drag a DTR along a surface, and I hate doing that. Reason being is there's so many inaccuracies that you're building into the system. For one, it's the lathe that's moving as you drag the DTR. It's the setup of the DTR. It's the lathe that might be moving the DTR incorrectly because you're using your hand wheels and all sorts of nonsense. The best way to set up things in a machining surface like this, when you have a known surface relative to a good backing plate, is of course an engineering square. And if you take this engineering square, you put it up against your chuck, and you just put it up against that surface that is your reference surface, and you don't see any dark or you don't see any light, you are spot on. And I tell you what, the human eye is amazing. You cannot get better than this setup. And of course that's one surface, so you've sorted it out like this. Now we need to sort it out like that. So any setup requires two surfaces. Now here's a tip. This surface is machined, and that's a reference surface, and we're going to use it for the rest of the build. But to get that surface, we use these bottom drain cock bosses. Now these surfaces, those bosses, is what you should be using for your second surface, because that's what you use to get that surface. What a lot of people do wrong is now they start changing their reference points, and that is just a bad idea. It makes all sorts of issues while you're machining. So what we'll do is we'll use the surface that we machined, and that looks fantastic. So that's that plane. And now we're just going to flip it around and we're going to do the other plane. And if we look inside there, you can see that that surface is touching both sides. Hey, that looks pretty good. All right, let's skim this. We flip it around. We're going to have a nice surface, and then we're going to do the most critical part of the whole build, the bore. Nice. Every workshop needs a surface plate. But look, who's got the money to spend thousands and thousands on a surface plate that has been ground to ridiculous tolerances? It's not necessary for the home workshop. There's a couple of things that you can use instead of buying an expensive surface plate that you can find typically lying on the side of the road. My surface plate I found literally on the side of the road when one of my neighbors decided to redo their kitchen. And what it is, it's one of these granite kitchen tops. It is perfect for a surface plate, and it has done me in good stead for many years. What you could also use is a nice piece of glass, a decent sized glass, sort of 6 to 10 mils, and then you just put a piece of wood behind it. Again, pretty good for the home workshop. This is how you check if it's okay. What you typically do is you take a flat edge, which would be a sort of engineering ruler, you hold it up like this, and if you don't see any light coming through, then you're good. If you flip it around, then you do this in various places in the surface plate, and you know that you're good. So a couple of interesting things. If it's wobbly on the one side and you flip it around and there's a hole in the middle, then you know that your ruler is skew. If it's flat on the one side and it's not flat on the other side, then you know your ruler is skew. If it's wobbly on both sides, then the chances are that it's actually the plate that's wrong. So that's typically what you're looking for. You're looking for no light coming through the bottom at every place that you measure. So let's check how close we were with what we've just machined. Now, what you do is you take the engineering square and you bring it up against what you've just machined, and you are looking for no light coming through. And that looks pretty spot on. Right, the next thing we need to do is we need to get the center of the bore, which we're going to machine next. So to mark out the center, a lot of people stick a piece of wood in and they mark it relative to whichever face you're working from. I use a slightly different technique. I use masking tape, and the brilliance of this method will become a little bit more apparent later. But it is much easier to work with. And of course, much quicker. The next step is finding the center line of the bore for lining it up on the lathe. Now, the most critical dimension on this next step is the distance from the valve chest face to the center line of the bore, because you do need space for your steam passages and all of that. Now, I personally don't like physically measuring from there to there. I normally pack pieces of metal up until I get the right distance, and then the distance from the surface plate to the edge there is exactly the right distance. And I typically design in metric, so it's really easy to find pieces of plate that stack up properly. Then if you just put it flat, you can draw a line at the correct distance. Then that is the critical line for the center line of the bore. Then all you need to do is find the center relative to the outer as cast surface. and you make a center mark at the average point of all of these as-cast surfaces on your critical dimension line. Now we can put this in the lathe and we can do some machining. This is where all that initial setup work is going to pay off. We have a decent reference surface here and we've just machined the back end. So what we do is if you tap that back end up against the chuck, now what you have is this casting is perfect in this orientation, but of course it can move like this and that. Let's just check that. So if we take our set square and we put our set square up against the back, and that's pretty good. There's no light, no darkness. That is fantastic. So now we know the casting is set up in this direction. That little mark that we made before is relatively easy to line up on the tailstock. And what you want is, you want it definitely on the line that we made from the valve chest surface. That's really, really important. And then you want it as close as possible to the average of the as-cast surface of the outside of the casting. And a nice way to check to see if you've got it right is if you turn on the lathe, you'll see that little mark is small. If that mark is too big, then you've got a lot of run out and you've got a problem. You need to sort that out. Let's machine this. Nearly forgot. The brilliance of using this masking tape to line up a casting like this is if you clamp it too hard, you'll see the masking tape move. Now this won't happen with these cylinders because I designed them to be relatively stiff and it's got a nice sidewall. But a lot of the cylinders that you buy sort of for the older designs have got a much thinner sidewall, and when you clamp it, it tends to distort the cylinder and then you're not going to get a good steam fit. So doing masking tape like this will show you very quickly if you're clamping too hard, because the masking tape will bulge. So bad news. One of my castings has a whole lot of inclusions on the one side, and that's why I hate casting gunmetal. But look, I'll get to that later. Nah! Oh, I need a cup of coffee. So coffee down the hatch, feeling a whole lot better. Now I actually do have a spare casting that I could use and I could machine, and I could show you guys that everything is running 100% in my build. But that's not how it works, and it wouldn't be fair on the beginner. Even an experienced builder will run into issues. Now it's actually really easy to solve a problem like this. In this case, a whole lot of inclusions inside the bore. What I've done before, and I actually did it on my very first loco, is I put a stainless steel sleeve in. Now that loco has been running for over 10 years and it works incredibly well. So what I'm going to do is the cylinder that machined well, we'll carry on with that, and I'll show you how to do sort of all the next operations with a good cylinder. But I will show you the bad cylinder where the problems might run in if you put in a stainless steel sleeve. So in that way you can see both options. Machining the sleeve is tricky because you have to deal with chatter. Machining a thin tube is a problem. It can give you a little bit of chatter. Also, when you design the tube, because that typically won't be in the drawings, you need to make sure that the bolt holes for the end cap don't hit the tube, because otherwise you're going to break taps. You also need to make sure that the tube is thick enough so that you don't end up with all sorts of horrible distortions. And there's a whole lot of design issues. Rule of thumb, don't go thinner than 2 millimeters wall thickness. Machining that sleeve without getting chatter, now that is a little bit tricky. Let me show you how to do that. Now before we go any further, we're going to have to deal with this chatter problem, and here's a top tip. If you just take a damp rag and you stuff it in to the tube that you're going to machine, it'll dampen all of that chatter and you're not going to have any problems. Nice. So unfortunately this casting was taken out of the chuck, and that creates a whole lot of alignment issues. Luckily we've been very good with keeping the reference faces and keeping them to the back of the chuck. So easiest way to set this up is just make yourself a little pointer that goes into the tailstock, and what you do is you push the casting up against the back of the chuck. Then you tighten your chuck jaws and you'll be very, very close to where you need to be. It's always prudent to check your reference surfaces, and that looks pretty good. So now this should be more or less right. The last thing we need to do is check that this is running true, because we're going to open this up and then work from there. Now we don't need fancy DTIs and DROs to line that bore up. All that you need to do is use my touch and engage method, and all that is you touch, you note the marking on your cross slide, you flip it 180 degrees, you note the marking, and you want it to be on 0 every time, and that's on all 4 chucks. And that looks pretty good. The final test is, of course, to take the lathe for a little bit of a spin, and you'll see very quickly if that bore is out. That's good enough.